In this section, we're going to talk about area and perimeter of polygons. And before we do, though, we're going to talk about two different types of polygons, just very briefly. We have convex polygons and concave polygons. Now, there's a technical definition for both of these, but kind of the way I remember it, concave polygons are caved in on a side, and convex polygons are not concave. Technically, if you could draw a line, if you took one of the sides and you extended it, you see how it would cut through the polygon? Whereas over here, if I take any of the sides and I extend them, none of them cut through the polygon. That's one way of defining convex versus concave. Another one is if I drew a line that stretched from one vertex to the other, you can see how this one is outside the polygon if I stretch from here to here. Whereas over here, all the sides are right along, the distances between the vertices are all right along the side. So another way of looking at concave versus convex, but again, concave, caved in, pretty straightforward. Perimeter. Perimeter is the distance around a polygon. Area, on the other hand, is how much a polygon covers up, right, on the grid here. And we're going to be dealing with mostly shapes on a grid for this section. One thing that students sometimes mistake is when they're doing perimeter, they'll be counting spaces, and I go 1, 2, 3, 4, 5, 6, 7, 8. I'm not going to count this last one because that's not a full box. No, it doesn't matter if that's not a full box. What matters is you're traveling along this edge. Imagine the grid was made up of city blocks. That's 1, 2, 3, 4, 5 blocks. That last block counts, even though once we turn the corner, we're kind of cutting at an angle here. All right, if you want to find the perimeter of this particular polygon, we just add up the lengths of all the sides. You can see the first two, AB and BC, we're just using that absolute value of the difference of the x and y coordinates thing that we did in the other section. So since AB is vertical, we have y sub a minus y sub b, which is 3 and negative 1. 3 minus negative 1 is 4, and the absolute value of 4 is 4. 4 spaces, which you could also just get by counting 1, 2, 3, 4. BC, on the other hand, BC is horizontal, so we take the difference of the x coordinates. X sub b minus x sub c. The x coordinate for b minus the x coordinate for c. So here we have negative 2 and we have 3. Negative 2 minus 3 is negative 5, and the absolute value of negative 5 is 5. And we can get that by counting as well. 1, 2, 3, 4, 5. The third side, however, is diagonal, and we can't count spaces on the diagonal, so we have to use the distance formula. So the distance formula, we take the difference of the two x coordinates and the difference of the two y coordinates. Right, so x sub a, x sub b, our x coordinates were, let's see, negative 2 and 3. Negative 2 minus 3. The difference of the y coordinates, y sub a and y sub c, we've got 3, and we've got negative 1. So 3 minus negative 1. And then we just figure that negative 2 minus 3 is negative 5. 3 minus negative 1 is 4. Then we square them, and remember, when we square a number, it's always positive. So negative 5 squared isn't negative 25, it's positive 25. We square numbers are always positive. And 4 squared is 16. And then we add together 25 and 16, and we get 41. Of course, then we have to take the square root of that in the end, and we're going to get a number that is a little bit bigger than 6, but not quite as big as 7. I do want to point out something here. You notice you got this negative 2 minus 3 here. You've seen that already up here, negative 2 minus 3. And here you've got 3 minus negative 1, and you've seen that already up here too. Right? In fact, here you've got your negative 5 and your 4. There they are. That is not a coincidence. Take this down here a bit. The distance formula is actually based on the Pythagorean theorem. And here, the Pythagorean theorem says when I have a right triangle, a squared plus b squared, those are the two legs, are equal to c squared. So in this case, a and b are 4 and 5, which we calculated that by finding the difference of the coordinates, or we could have just counted spaces. And then 4 squared plus 5 squared. 4 squared plus 5 squared, 16 plus 25, 41, square root of 41 over here. So the distance formula is just sort of it's a use of the Pythagorean theorem in the coordinate plane. If you're interested in more of that, we'll definitely have some opportunities to explore it for some additional points. Anyways, going back to our perimeter problem, we've got AB plus BC equals CA. That was our, go all the way back up here at the top. So, yeah, there was our original perimeter is the three sides added together. Follow my line down. And here we are. So AB was 4, BC was 5, and CA was square root of 41. So when we add those together, 4 plus 5 is 9. Now you can't just add 9 and 41 because this is the square root of 41. So the best exact answer for this would be 9 plus the square root of 41. And let someone else turn this into a decimal and round it off where they think is most appropriate. But if you needed to, you could say that the perimeter was approximately equal to wavy equal sign 9 plus 6.4, which is equal to 15.4. The whole perimeter is approximately 15.4. Next, let's look at area. That's the amount of space. I guess space might not be the best word, but the only real way to talk about area is to say area. But the amount of space covered by a polygon. So not the distance around it, but what does it cover up? So we have an example here with a triangle, and the formula for the area of a triangle is 1/2 base times height. So we need to find the base, that's the distance from A to C, and we need to find the height, the distance from B to D. Oh, by the way, clearly you could just be counting spaces on pretty much all of these, but we're actually going to do the math in case you run across a situation where maybe this is some sort of strange fraction or decimal or something like that. All right, so the base, AC, that's a horizontal line, so we're going to use the difference between the x-coordinates, which are, oops, wrong tool there. We've got -2 and we've got 6, so -2 minus 6, which is -8, and the absolute value of -8 is 8. Notice, by the way, if I had subtracted the other way around, if I'd gone 6 minus -2, I would have got a positive 8. So the thing with the absolute value is, it's so you don't have to worry about which coordinate comes first. You can do either one because the distance is always positive. So the absolute value makes it always positive. Anyway, the base is 8. Now we're going to look at the height. Well, the height is a vertical segment in this particular case, so it's the difference between the y-coordinates. So we have 4 and we have -2. So 4 minus -2, well, that's the same as 4 plus 2, that's 6. And so the height is 6. So our area of our triangle, 1/2 base times height, is 1/2. AC is the base, AC. The height is BD, BD is the height. And so then we plug in our numbers that we got here. AC is 8, comes from up here. And BD is 6, comes from over here. And 8 times 6 is 48. Half of 48 is 24. And that's our area. All right, moving on. Here we're going to look at another example of area. This time we're dealing with a rectangle shape. So the formula for the area of a rectangle is just base times height. The base is DC. So there's point D, there's point C. By the way, in a rectangle, the base could have been DA or AB. It doesn't matter. Any side can be the base. All right, DC. So since DC is a horizontal segment, to find its length, we're going to look at the difference between the x-coordinates. X-coordinates are -2 and 4. -2 minus 4 is -6, and the absolute value of -6, its distance from 0, is 6. Next, we're going to find the height. That's AD. AD. Now, of course, if DC is the base, we could measure the height as AD or BC. It doesn't matter either way. And in fact, the numbers would be the same. Notice, to find the height, since it's vertical, we'll be looking at the difference between the y-coordinates, and the y-coordinates are 2 and -2, and over here 2 and -2. Those same numbers. 2 minus negative 2 is like 2 plus 2. Oh wait, 2, what did I do here? That's wrong. Goodness sakes. 2 plus 2 would be positive 4, not negative 4. Look at me. Let's just go ahead and fix that. That's positive 4. Okay. So positive 4. I'm going to scooch this down just a little bit here. So area of a rectangle, base times height. The base was DC. The height was AD. Notice with DC and AD, no lines over top. DC and AD are numbers, not the names of the segments. They are numbers. So DC, the distance between D and C, was 6. And AD, the distance between A and D, was 4. And 6 times 4 is 24. So our area is 24 square units. Hey, wasn't that the same as the triangle we just did? Interesting. All right. Let's pause for a moment, and then we'll move on. All right. I want to show one last example of area here. I'm not going to work out all the math, but I just want to explain that you can actually find the area of pretty much any weird polygon in the coordinate plane using what I call a boxing in method. The boxing in method tells us to simply draw triangles around the outside like such, so that I take this sort of weird shaped polygon and I'm going to box it in to make a big rectangle. And we know how to find the area of a rectangle. That's just base times height. And we know how to find the areas of each of these 3 triangles. It's just base times height times 1/2. Base times height times 1/2. And this one here, it's upside down, but it's all the same. We could call this the base and this the height. Base times height times 1/2. And then all I'd have to do is find the area of the big rectangle, area of BEFG, and I just subtract the areas of the 3 triangles. And I could do that with all sorts of shapes. Here is a parallelogram. I just surround it with 4 small triangles, find the area of the big square, subtract the areas of the 3 triangles. Here's a triangle. I could have used base. This would be the base. That would be 3 units, and the height would be right here. I could have done base times height, or I could just turn it into this rectangle, a special rectangle, by the way. It's actually a square, and then just surround it with these 2 triangles, find the area of the square, subtract the area of the 2 triangles. Whatever's left over is in here. I've got, here's a triangle. This type of problem comes up sometimes. Sure, the area of a triangle is base times height times 1/2, but it's hard to find the base or the height of this triangle. It's especially difficult. It requires a lot of steps. We'll be doing something like this later, but it's not easy. The easier way would be to just box it in. So you've got this rectangle, find the area of the rectangle, calculate the area of the 3 triangles, and subtract. You can even do it with all sorts of extra oddball weird shapes like this one here. Notice when I box it in, not all the surrounding areas are triangles, but I've got like there's a triangle here, there's a small triangle here, there's a square there, there's a triangle down here, and then I've got this 2x1 rectangle. So still, I'm surrounding the shape with easy to calculate shapes in order to blow it up into this big box or rectangle. I can easily find the area of the rectangle, and I can easily find the areas of all the little surrounding shapes. I subtract, and that gives me the area of whatever's left over in the middle. It's a very useful method, which we're going to be using. We're definitely going to be using this method later on. So just to recap, perimeter and area in the coordinate plane. Perimeter is the distance all the way around an object. Sometimes requires us to use a combination of simply subtracting coordinates or maybe using distance formula. Area is how much space something covers up. And we've got some basic formulas for triangles and rectangles, and we have this method called the boxing in method that we can use for various other kinds of shapes. All right,